Okay, so now we will discuss the difference between absolute pressure and gauge pressure, and also discuss the concept of pressure differentials. Pressure differentials is how you're able to crush this extremely strong pressure vessel you see in this picture using only the atmosphere. Right, the atmosphere is 14.7 pounds per square inch. If you have a lot of square inches, that's a lot of force. So we can talk about how that works in a moment, and we'll show some cool videos. But first, let's talk about absolute and pressure and gauge pressure. So it turns out that most pressure gauges are not calibrated to tell you the true or absolute pressure. Right? So if you have a tire pressure gauge like this one, you can maybe see in the picture that the black numbers are in psi and the red numbers are in bar. All right, on this pressure gauge. So if you were to go and check the pressure on your tires, your pressure gauge is not telling you the true or absolute pressure. It's not telling you newtons per square meter, or it's not telling you the true pounds per square inch of the pressure inside that tire. What it's telling you is the difference between the pressure in that tire and the atmospheric pressure. Okay, so to be clear on our terminology, the absolute pressure is the true pressure, where zero pressure corresponds to a total vacuum, where you have no molecules bouncing around, hitting the side of your container. There's just no pressure at all, right? And that's a zero pressure point. And any pressure above that we measure in terms of newtons per square meter or pascals. And so the absolute pressure is the gauge pressure plus the atmospheric pressure. If you're on the Earth and you want to figure out the pressure inside your tire, your gauge is going to read the gauge pressure. If you add to that the atmospheric pressure, that tells you the absolute pressure inside your tire. Right? The gauge pressure, the 0 point, when it says zero pressure, it's not actually zero pressure. It's been calibrated such that zero pressure corresponds to 1 atmosphere. Right? That corresponds to 1.013 times 10 to the fifth pascals, or 14.7 pounds per square inch. Right? So a gauge pressure gauge is going to tell you the pressure relative to the atmosphere. And that means it can be positive or negative, right? If the pressure inside your tire is greater than the atmospheric pressure, it's going to tell you a number greater than 0. If the pressure inside your tire is exactly atmospheric pressure, it's going to tell you 0 pressure. And if the pressure inside a vacuum vessel of some kind is less than atmospheric pressure, even though there is still pressure in there is still molecules bouncing around, the gauge pressure is going to tell you negative pressure. Okay. Just a little bit more discussion of this. So again, if you have a tire and you read in the tire it says 32 psi, we mean that, again, the pressure inside that tire is greater than the atmospheric pressure by 32 psi. So since atmospheric pressure is equivalent to 14.7 pounds per square inch, if I want to calculate the absolute pressure, I need to add the atmospheric pressure plus my gauge pressure to find the actual absolute pressure inside that tire is 46.7 psi. Okay. Now, there's still, if you have 46.7 psi of pressure inside your tire, you still have 14.7 psi outside your tire pushing on the outside of your tire, right? So the pressure differential is still 32 psi, right? So that's kind of why we use gauge pressure. And yeah, I think everything else on this slide we pretty much discussed already. Okay, so now let's talk about pressure differentials. And if you create a partial vacuum in a container, if you decrease the pressure in a container to less than atmospheric pressure, you now have atmospheric pressure outside of a container, something less than atmospheric pressure inside a container. You have a pressure differential. You can now crush some really strong containers. So let's quickly show some videos on this. Okay, so the first one is just using a soda can, and the soda can has some fluid, some water in it. It's open on the top. He's poured some water in the soda can, and he's going to put it on a Bunsen burner and heat it up. Let me skip ahead a little bit here. Okay, at some point it starts to be kind of steaming. Once it's steaming, he takes the can, flips it over, and puts it in some cold baths of water, and you see the can just gets crushed. I think we'll see another view of it now in a second here. Okay, so the can is filled with steam, right? It's filled with hot steam. It puts it in the cold water, and that suddenly decreases the pressure inside the soda can to less than atmospheric pressure. Okay, when he does that, it's a little slow here. The can crushes. There we go. Okay, so the atmospheric pressure is greater than the pressure inside the can, and the can gets crushed. You can also do this with a steel drum. So they've done the same thing here. They've heated up this steel drum and now put it in this cold pool, and they're spraying cold water on it. And let's see what happens. Whoa. Okay, so that is a pretty powerful crush just from the atmosphere crushing that steel drum. So that's pretty neat. And you can do the same thing. In this case, they're not using hot, steam to decrease the pressure. This time they're just using a pump inside this very strong pressure vessel. They're just going to be decreasing the pressure inside the pressure vessel. As they do so, there's some amount of pressure inside the vessel, some amount of pressure outside the vessel, but there's a pressure differential. The atmospheric pressure is bigger than the pressure inside, and this whole vessel is going to crush. Okay, there it goes. So pretty spectacular. There must have been a weak point of some kind on this side of the vessel, and that side of the vessel crushed. But that's pretty neat. I don't know if they have any more slow-mo videos here. So that's atmospheric pressure just totally crushing this pressure vessel. And lifting this probably many-ton object off the ground. You can think about the physics of that on your own. That's kind of fun. So, okay, that's neat. So back to our videos. Back to our presentation here. Okay. So talking about what caused this pressure vessel to get crushed. This was not a vacuum force. It was not that the motor, the vacuum sucking air out of this container was not so strong that it crushed this the container. This pressure vessel failed. It was crushed because the atmosphere crushed it. Right. Inside the pressure vessel was lower pressure than outside. If you have a pressure differential, that's an enormous amount of force, right? Pressure is force per area. So if you have a bigger pressure on one side of a wall than another side, then there's going to be a bigger force on one side of the wall than the other. If you have a net force, that can cause things to move, right? So we can actually go through an example of with this pressure vessel. So outside the pressure vessel, what is the gauge pressure? Well, the gauge pressure is just 0 pascals, 0 atmosphere, 0 psi. If you had a normal pressure gauge outside this pressure vessel, even though the real pressure is 1 atmosphere, your gauge is going to tell you 0 atmospheres or 0 pascals or 0 psi, because that's what it's calibrated to do. It's calibrated to say 0 psi when it's in 1 atmosphere of pressure. But in absolute pressure, the actual outside pressure is 1 atmosphere, or 1 times 10 to the 5th pascals, or 14.7 pounds per square inch, which, if you do the math, corresponds to 2,000 pounds per square foot. Right? So absolute pressure of the atmosphere is enormous, 2,000 pounds per square foot of pressure. And this is the pressure that's affecting you right now. This is the pressure that is acting on your body. It's acting on the walls of your house. Luckily, it's acting equally on the inside and the outside of the walls of your house. Okay. At the beginning of the experiment, the pressure inside the pressure vessel is also 1 atmosphere, right, or 2,000 pounds per square foot. But say let's remove some air from inside the vessel. If we decrease the pressure inside the vessel to half an atmosphere, now the pressure inside the vessel is only 1,000 pounds per square foot, where the pressure outside is still 2,000 pounds per square foot. Right, so that's a huge pressure differential. There is more force pushing on one side of the wall than the other side of the wall. Okay. When I decrease my absolute pressure to half an atmosphere, my gauge pressure is now reading minus 1/2 an atmosphere. Right. My gauge pressure is now negative. Right. Even though there is still positive pressure inside that vessel. So we could do a kind of a back of the envelope calculation of how much force is affecting the cylinder. So let's just basically, if you want to figure out the net force affecting a cylinder, let's just figure out the total force of the outside atmosphere pressing in on the cylinder and subtract from that the force of the gas inside the cylinder pushing on the walls of the cylinder. All right, that'll tell us kind of the net force on that cylinder. So force is just pressure times area. So if I do pressure outside times the surface area of the cylinder, that tells me the total force affecting the outside of the cylinder. If I do the total pressure inside the cylinder times the surface area of the cylinder, it tells me the total force affecting the inside of the cylinder. Right, so this is my pressure differential. Pressure outside minus pressure inside. If I multiply that by the surface area of the cylinder, it tells me the force, the net force affecting that cylinder. Okay, so here are the numbers we came up with in the previous slide. 1 atmosphere outside, half an atmosphere inside. To calculate the surface area of the cylinder, basically I have to use the surface area of the open cylinder and add to that the surface area of the kind of the ends of the cylinder, right? The two kind of circular ends of the cylinder. So again, here's my pressure differential. Surface area of a cylinder is 2 pi r, 2 pi times the radius times the length of the cylinder. The surface area of the circular end is pi r squared. Multiply that by 2 because I have 2 ends. And now I can plug in some just theoretical numbers where the radius of the cylinder is 3 feet and the cylinder is 25 feet long. And when I do that, I get that the net force affecting a cylinder is 5 times 10 to the 5th pounds, or 279 tons. Right? So an enormous amount of force is affecting the cylinder, which causes it to crush. Right? So that's just kind of a back of the envelope calculation, but it's kind of a fun one that you can do. We would typically do this type of problem more with something like a window or something like that. If you have a window in the house, it's a nice flat area, you can figure out the net force on that window just by considering the pressure outside, the pressure inside, and the area of the window. Some fun examples of this when in the ocean. In the ocean, as you know, as we go dive deeper and deeper in the ocean, the pressure increases linearly. And so if you're about 1,000 meters down in the ocean, the pressure is about 100 atmospheres. Right? That's an enormous, enormous pressure that will crush almost anything. Right? So how is it that there are fish that live under the ocean that deep? Anglerfish live 1,000 meters under the ocean, where the pressure is 100 atmospheres. So how can that be? Well, there's no pressure differential because they have 100 atmospheres of pressure outside of the fish. They also have 100 atmospheres of pressure inside the fish. Right? There's no air inside this fish, and the water inside the fish is incompressible fluid, just like the water outside, and that's how these fish can survive. Another really fun example is, well, I guess not so fun, but relevant, is hurricanes. What a hurricane really is an area of extremely low pressure. Right? So if you measure the pressure at a given location as a hurricane passes by, on the y-axis here we have the pressure, on the x-axis we have the time. You can see that the pressure is kind of slowly decreasing, and then as you get close to the eye of the hurricane passing over you, the pressure drops down spectacularly, right? So that's what a hurricane kind of looks like as it passes over you. And that big decrease in pressure is what causes extremely high winds, but it also can cause huge damage to your house, not just from the extreme winds, but the fact that outside of your house there is really low pressure. Inside your house you still have atmospheric pressure, right? So you have a pressure differential. So that can actually make the air inside your house push the roof off your house. It's not necessarily just the wind blowing the roof off your house. The actual air inside your house can push the roof off your house because the pressure of the atmosphere is now dropping down so low around your house. Okay, so just some more examples of pressure differentials. And that's it for this video.